All right, I'm back. All right, so we want to notice that. So first of all, why did we separate these out? Like, it seems like we could have just kept it as um, instead of having this sort of awkward exception where if I is equal to j, then we do this other thing. The reason why this matters is because basically we this is normalized. So the expected value of xi minus mu is 0, and the expected value of xj minus mu is 0, because approximately a point is equally likely a point is equally likely to be on one side of the mean or the other. That's not literally true, because you could have an asymmetrical distribution, but it's like the point mass, the mass of the weighted average is as elements from weight of the weighted average is as likely to be on one side of the mean as the other. So on expectation, xi minus mu is equal to 0. However, that is not the case for xi minus mu squared, because this, whether or not if xi is not exactly mu, regardless of whether it is positive or negative, the squared version is going to be positive. So the value of this is actually different than 0. In fact, this is just, again, our definition of variance. So we can substitute the sum from I equals 1 to I equals n is sigma squared. Plus this, right? We're just importing this formula. Well, I guess there's an expectation there. That seems important. Well, actually, it doesn't matter, because luckily, all of this is in an expectation. Yeah, right. We had an expectation. We had this inside of an expectation, and because expectation is linear, we can just take the expectation of both of these sides. It's definitely ugly and awkward. So if we take the expectation of both sides, then we have sigma, which resolves the expectation, by the way, right? The expectation is part of the sigma, plus an expectation of something that in expectation is equal to 0, and something that in expectation is equal to 0, which is equal to 0. Another way to think about this is either of these is possible for xi to be slightly bigger than mu, in which case this term will be slightly positive, or it could be slightly smaller than u, in which case this term will be slightly negative. And the same is true of this term. So it's possible that, like approximately speaking, either both terms will be positive, or both terms will be negative, or one term will be positive, one term will be negative, and those cancel each other out. And so because of this, the expected value of this sum is equal to 0. Oh yeah, one thing that's important is because this is a sum, we're actually distributing the expected valueness to each element in the sum. And that's how we end up with this. And so overall, we end up with, going back to here, equals 1 over n squared times the sum from I equals 1 to n of sigma squared. And since this is a constant, that's just equal to 1 over n squared times n sigma squared, right? Because we're taking sigma squared once for there's no actual xi here, so we're just iterating through and we're saying sigma squared plus sigma squared plus sigma squared plus sigma squared n times, and so this looks kind of like 6, but it's actually sigma, and so we have n sigma squared, which means that we can cancel out this squared, and we have 1 over n sigma squared, and that is the variance of mu hat. Yep, the sample mean. The sample mean is equal to 1 over n. The variance of the sample mean is equal to 1 over n of the variance of the whole population. Okay, cool.